This video illustrates the problem-solving procedure for a problem in the kinematics of a rotating object. And we will see that the process is very similar to the process we developed for an object in translational motion. The problem says, an oscillating fan is spinning at 655 revolutions per minute when the switch is turned off. The fan blades come to a stop in 6.75 seconds. And we're asked a number of questions about the situation. How fast was the fan spinning initially in radians per second? What is the angular acceleration of the fan? And how many times does the fan spin before coming to a stop? The process for solving a problem in the kinematics of a rotating object is very similar to the process that we used in solving problems in linear motion. As with linear motion, there are 6 variables involved in the kinematics problem, and they're similar to their translational versions, just different symbols. Instead of linear position, x naught and x final, we have angular position, theta naught and theta final. Instead of linear velocity, v naught and v final, we have angular velocity, omega naught and omega final. Instead of linear acceleration a, we have angular acceleration alpha. T is the same whether we're talking about rotational or translational motion. So the first step in this problem-solving process is to read the problem and figure out what data we are given. In this case, we are told the initial angular velocity of the fan, 655 revolutions per minute. That's not quite in the right units. We're going to have to work on that, but we'll write it down for now as 655 revolutions per minute. We're told that the fan comes to a stop, and that means the same thing for rotational motion as it did with linear motion, that the final velocity is 0. And we are told that this takes a time of 6.75 seconds. Now, the first thing we should do before we go any further is to make the unit conversion that we are asked for here and ask what is the speed of the fan initially in radians per second. This is an exercise in unit conversion, and so we follow our process for unit conversion. We want to get rid of revolutions, and so we put that on the bottom and replace it with radians. We put that on the top. For 1 revolution has 2 pi radians. We're not quite done yet because we have to get rid of minutes and replace it with seconds. And 1 minute has 60 seconds, so the minutes cancel. And that leaves us with an initial angular velocity of 68.59 radians per second. Now, I'm leaving that in 4 significant figures. We would report this as 68.6 radians per second because we have 3 significant figures in this problem. I'm leaving it in 4 significant figures to reduce our rounding errors. Now, the second step in the problem-solving process is to, again, read the problem and figure out what we are asked for. In this case, we're asked first for the angular acceleration. We're asked for that outright. And in the final question, we're asked, how many times does the fan spin as it comes to a stop? Well, that is really asking for the final angular position. For convenience, we'll call the initial angular position 0. Then if we find the final angular position, we can figure out how many times the fan spun. So we figured out what the problem is asking us. The third step in the problem-solving process is to figure out what is irrelevant to your current problem, and that will guide you to the right tool. Well, initially, we do not know the final position, and we are asked for the angular acceleration. So for this first part, finding the angular acceleration, the final position is irrelevant. And so, as we did with linear motion. We turn to kinematics equation number 1. Notice it has the same form as the linear kinematics equation, except we're using angular velocities and angular acceleration. Well, we know that the final angular velocity is 0. The initial angular velocity is 68.59 radians per second. And we know that it takes 6.75 seconds. Solving this equation for alpha, we get alpha equals negative 10.2 radians per second squared. Notice the negative sign here on alpha indicating that we are slowing down. It means the same thing in rotational kinematics as it did in translational kinematics. If the sign of the acceleration disagrees with the sign of the velocity, it means the object is slowing down. This is going to be important for us. Now, the final question asks us essentially to find the final position of the fan. If we can figure out how many radians the fan has rotated through, we can translate that into a number of revolutions. And so we can turn to the second kinematics equation to find that out. Since we know everything here in this equation, we just figured out alpha. So we can calculate that final angle. 0 is the initial angle. The initial angular velocity is 68.59. The time is 6.75. Notice here when we put in the figure for acceleration, we have to keep that negative sign in there. And the time, 6.75 seconds, is squared. Calculating this out, we get a final angle of 230.6 radians. That is the angle through which the fan blades spin as they come to a stop. Now, our task is not yet finished because we were not asked for the number of radians, we were asked for the number of revolutions. But finding that is a simple matter of unit conversion. This time we put radians on the bottom and revolutions on the top. The radians cancel out. One revolution has 2 pi radians, so we take 230.6, divide by 2 pi, we get 36.7 revolutions. So our answer to 3 significant figures is that the fan spins 36.7 times before coming to a stop.